Yeah, that was stupid. Yeah. It's whole bunches of people have been trying to tell me to record, and I realize that it's only Tanya's message that got through. Whoever tried to tell me, thank you very much. I think it was Meda. Thank you, Meda. Yeah, sorry about that. So now let's just put the harmonic oscillator problem aside. I will try and see if there are some other interesting problems which I can give to you to solve in the harmonic oscillator problem thing. And of course, we have to I mean, this is up to me. We will find out a day in which we can discuss this whole bunch of problems. All right. So let me now go ahead and talk to you about the delta function potential. And as I told you, this is not something that we did as a part of um, our one-dimensional problems. Okay, and I think the now where we have really handled the delta function potential. So it's a little important that we know how to basically handle it, and more importantly, as a part of this course, how to handle problems on the delta function potential. So let me share my iScribe with you. Okay. Yeah, just 1 second. Hopefully that's taking the full page. Just 1 second. Okay. So essentially, how do you define a delta function? Okay, so let's start off from there. All right. So we will talk about the delta function potential. This is visible, right? Yeah. Okay. And essentially, please remember your delta function. So this is what we are going to use is the Dirac delta function. And how do you actually define the Dirac delta function? You say delta of x is equal to 0, okay, if x is not equal to 0, and it is infinity if x is equal to 0. Okay, so it basically is 0 at all points except at a singular point. All right, so this is what your delta function potential is. Now interestingly, there is another uh, important so this is only an incomplete definition. What makes the definition complete is that your integral from minus infinity to plus infinity of this delta function potential, okay, should be equal to 1. All right, so this is the two of these things together. Okay, this whole thing is essentially your definition. Okay, so one cannot leave out the second part. Okay, that's extremely important, that yes, it does go off to infinity at a single point, but if you did an integration, okay, from minus infinity to plus infinity, so for the entire range of the variable, you should get 1. All right. Now, just a few important points about the delta function potential. One is that, your f of x, if you have a delta of x minus a, right, then this would actually be, you could write it, you might as well write it as f of a x minus a. Okay, you might as well write it like this. Okay, and then of course, if you did an integral from minus infinity to plus infinity of f of x delta x minus a dx, okay, then this would essentially become f of a integral minus infinity to plus infinity of delta x minus a dx, which will of course be nothing but f of a. So you will find it's actually this form. This is kind of pretty useful. All right. Okay, so now what are we going to do? We are essentially going to consider a potential of the form. So let me just write it down. Consider a potential of the form. So now I'm going to incorporate the delta function potential, all right? And what is this? This is essentially V of x is going to be equal to minus alpha delta x. Okay. So as you can so now let me just make very clear. Your alpha is a positive constant. Okay. So this is important. So what does it essentially mean? It means that your function, your potential is zero everywhere. So essentially the particle is going to be a free particle, all right, for x less than zero and x greater than zero. And exactly at x is equal to zero, this thing goes off to minus infinity. Okay. Yeah. So it is going off to minus infinity. There is a role of the alpha. Okay, you will see as we go along. Okay, it may seem why am I even bothering with the alpha? There is a role. Okay, so let's see that. So what we are going to do is that it's very interesting. You will find there is exactly one bound state for this. Okay, you may think that, hey, it's an infinitely deep potential, how many bound states am I going to get? Okay, so this is a pretty interesting question. So please keep this in your mind. You will find there's exactly one bound state. Okay, so question is, how do you go about solving for this bound state? Okay, so let's have a look at that. So let's solve for uh, bound states. Okay, I will not here kind of preempt the whole thing by saying, okay, there's only one bound state. So what do we mean by bound state? Of course, we are looking for negative energy solutions, right, where you have to provide energy in order for the particle to be free. So now let's write down the Schrodinger equation. Okay, so one dimensional system, so I can always write in total derivatives. Okay, and then you have your psi minus alpha delta x psi is equal to E psi, right? Okay, so now what we will do is we will go for, so remember, I mean, whether E is positive or negative, the same Schrodinger equation, of course, holds. Okay, I should have actually written that later, but doesn't matter. Okay, so this is your Schrodinger equation, what I have written over here. And then let's look for the E less than zero solutions. Fine. So now for x less than 0, we know that v of x is equal to 0. Correct? Yeah, this is basically it. So essentially you'll have h cross square by 2m d square by dx square psi is equal to E psi, which implies, okay, so let me just continue on the same line itself. Your d square by dx square psi is equal to 2 me h cross by h cross square. I'll have a negative sign here, okay, psi, and then of course you will have essentially your d square psi by dx square. Okay, so remember your e is negative, right? So we'll write it as some kappa square psi, and where your kappa is going to be essentially minus 2 me by h cross square under root, right? Yeah, so this is what you get. So what's your solution now? Essentially, so remember your kappa is going to be real and positive. Okay, so this anyway, these are all no-brainer things. Okay, all of you know this. So therefore your psi of x is going to have a solution a e to the power of minus kappa x plus b e to the power of kappa x, right, for x less than 0. Now let's look at the situation when x is going to minus infinity, right? Because this is, so when x goes to minus infinity, please remember which one is going to blow up. It is essentially your a to the power of e minus kappa x goes off to, tends to infinity, right? Okay, so this implies that your a you have to put as 0. Correct? So thereby your solution is psi x should be equal to b e to the power of kappa x. Okay, so please remember for x less than 0. Remember. Okay, so this is your valid solution. All right. So now let us look at the situation. I will have to change the page. I'm sorry. Okay, because, okay, so let me just do it here. Okay, so now the situation is for x greater than 0. Okay, you can do the same thing again, and then you will get essentially your psi x. You will find your psi x is equal to, let us take some f of e to the power of minus kappa x plus g e to the power of plus kappa x. Now in this is for x greater than 0. So when your, it has to be bounded when x goes to infinity, all right, then you will find that your g e to the power of kappa x essentially goes off to infinity, which implies that you should take your g equal to 0. So therefore your psi of x is nothing but f e to the power of minus kappa x for x greater than 0. Okay, so now what do we have? We have for psi of x is equal to b e to the power of kappa x for x less than 0. So obviously now we need the two wave functions to be equal, all right, when we have x equal to 0. So continuity, right? So this is now how we are going to find out the relation between b and f, all right? So okay, so now, so there, so boundary conditions at x equal to 0. All right, so that's one. So the first one is, of course, your psi of x must be continuous. And what is the second condition? The second condition is that your d psi of x by dx must be continuous. Okay, so it must be continuous, but sorry, this is my problem when I start doing these ups and downs, I can't stop. All right, yeah, must be continuous where except, okay, so let me say except except when, okay, v of x goes off to infinity or minus infinity, it doesn't matter. Okay, yeah, so please remember these are your boundary conditions. Now let us go for the first one. Okay, so essentially psi of x is equal to b to the power of kappa x when x is, okay, I need not have written this, doesn't matter, f e to the power of minus kappa x when x is greater than 0. Okay, so obviously from the boundary conditions, uh, so therefore b must be equal to f. Okay, yeah, so this is essentially the first boundary condition. Okay, from the first boundary condition, this one. Okay, so the b must be equal to f. So now what has happened, your psi of x will thereby be equal to b e to the power of kappa x when x less than 0, b e to the power of minus kappa x when x greater than 0. Now question is, what is b? So what is b? Okay, so this is what we need to find out, right? um, so let us so before we do that, let me just plot the function. Okay, so the function looks something like this. Okay, so this is a little important to keep in mind. So this is of course your x is equal to 0. This is your x-axis. All right, and this is your psi of x. All right, so just keep this in mind because anybody shows you something like this, you should know. So okay, it goes up like this and then it comes down like this. It's going to be bounded. Okay, the thing is going to be bounded. All right, and as you can see, your d psi by dx is of course not going to be continuous. All right, it's obvious there's a cusp over there, so it's not going to be continuous, but your psi of x is continuous. Okay, at x is equal to 0. So keep this image in mind, please, because you should remember this is how a wave function looks when you have a delta function potential. All right. Okay, so let's now go further. All right, and what we will do over here, okay, we will so this is a trick which you can pull. You integrate, okay, the Schrodinger equation just to make a little more headway. All right, Schrodinger equation from minus epsilon to plus epsilon, okay, and then take limit epsilon going to 0. Okay, so this is how we will probably get a handle on B. All right, so this is a trick that you're pulling. You're going to integrate the Schrodinger equation itself. So let's now have a look at it. So what do we do? Of course, the first term h cross square by 2m, that's a constant. Then you have an integration from minus epsilon plus epsilon of, what do? We have the double derivative of psi of x dx. Okay, so this is the first term. Then you have, of course, your potential, right? So minus epsilon to plus epsilon, and then you have, I've taken the negative sign already outside, then you have your delta x dx. Excuse me. Sorry, I made a mistake. You'll have to put in the psi of x dx, right? And then you have over here integral minus epsilon to plus epsilon. You have essentially e psi of x dx. Okay, so this is what you have. Just excuse me. Right. So now here, so over here we will get h cross square by 2m, and then you will have a d psi x by dx, correct? And of course you'll have to take this between the limits of minus epsilon to plus epsilon. Then here, what will we get? Our alpha is a common thing. So you will get essentially minus epsilon to plus epsilon. Then you will get your delta x psi of x dx. So essentially you should get your psi of 0 over here, correct? Now think about what your psi of 0 should be. You will realize that it has to be B, correct? Yeah, so this is basically the way we are going to get a handle on B. Is equal to, and then your E is also common, and here you will get again minus epsilon to plus epsilon psi of x dx. Okay, so I have to change pages now. I'm sorry about this. I wish I could just continue forever. You know, I don't know how that is possible. Maybe you should have a just a scroll up, rather than having to change pages. Yeah, they could have done that in the software. I don't know why they had to change it. It would be easy on you guys also, right? Fine. So now let's go further. So what we are doing over here, so let me just repeat the last step over here. Okay, it will be make life easier for me also. So h cross square by 2m, I have, yeah, your d psi x by dx from minus epsilon to plus epsilon. And then we had what? I've changed notation everywhere. Minus alpha And then we had integration minus epsilon to plus epsilon. If I'm making mistakes, please tell me, guys, okay? Dx, I think psi x dx, right? And then we have over here e, we took out common, and then we have an integration from minus epsilon to plus epsilon, and then we have psi x dx, right? Now, okay, so I hope I rewrote that step correctly. And now what we will do is essentially, um, so look at this situation here, okay, this guy, okay, we will say essentially, if you took your epsilon tending to 0, since psi of x is continuous, this should go to 0, okay? So we are going to say that this term is essentially going to go to 0, okay? I hope everybody buys that logic. Psi of x is continuous. So obviously, if I take the difference between psi of plus x and psi, or the integration of psi of plus x and minus x, okay, essentially I should get a 0. All right. So this term I'm going to ignore. And what I have now over here, I have essentially, I will write it down as d psi x dx from plus epsilon to minus epsilon is going to be, so there's a negative on, sorry, it will become, excuse me, I just don't know why I'm getting this irritation in my throat. I'm sorry, it must be really irritating you people also. So I will get is minus 2m alpha by h cross square, correct? And then I have an integration. So this actually from minus epsilon to plus epsilon. Okay, I don't know why I've written this again. It doesn't matter. Psi of x, okay, delta x dx, all right? And this, you will realize, will be essentially minus 2m alpha by h cross square. It should be essentially nothing but psi of 0. Okay, this I've taken from this delta function, properties. Uh, but it's citing one of the properties I put on the very first page when we started discussing delta function potentials. So this is how it works out. So therefore, this guy, I'm going to write it as delta of d psi x dx is equal to minus 2m alpha by h cross square psi of 0. Now what you do realize that psi of 0 is essentially b, right? So therefore, yeah, so now so this is going to be essentially minus 2m alpha by h cross square b, okay? Also now for x less than 0, you'll realize that your psi of x is going to be equal to b e to the power of kappa x, right? This is what it is. So now, which implies that d psi dx is going to be nothing but b kappa e to the power of kappa x, correct? So now limit extending to 0 from the negative side, okay, of d psi dx is going to be essentially b kappa. You can take this out. Then you have, yeah, so it is going to go to 1, right? So it will be just b kappa, right? Everybody, I hope, agrees to that. Let's write from the other side. For x greater than 0, your psi of x is going to be equal to nothing but b e to the power of minus kappa x, which implies that your d psi dx is going to be b minus kappa e to the power of minus kappa x. Okay, so therefore, a limit of x going to 0 from the positive side, your d psi dx, the limit will be nothing but minus b kappa. Okay, yeah. So now, what is your delta d psi by dx should be equal to thereby nothing but d psi dx. How do I write it? At plus epsilon minus d psi dx at minus epsilon, and this will be essentially plus epsilon is minus b kappa, and this is going to be minus of b kappa, right? So it is going to be minus 2b kappa, right? So now let us go put it back into this equation here. All right. So what will we get now? We will essentially get on the left hand side. So let me just write it down once again. D psi dx is equal to minus 2m alpha by h cross square b. So implies that minus 2b kappa is equal to minus 2m alpha by h cross square b. Okay, so nicely enough, our normalization fellow just cancels out and we get a handle on kappa, right? So what we have over here is now your kappa is going to be nothing but m alpha by h cross square. Okay, it's a positive value. Yeah. So your kappa, if you remember, was nothing but root under root minus 2me h cross square, all right, isn't it? Which is now going to be nothing but m alpha by h cross square, which implies that your 2me by h cross square will be, okay, let's keep the minus sign. It's going to be m alpha by h cross square whole square, correct? Let me see if I can squeeze in that value of E over here itself. This implies that E is going to be nothing but minus, you can have h cross square by 2m into m alpha by h cross square whole square, correct? So let me change the page and write down the E on the next page. So you realize that you're going to get only a single bound state, right? So your E therefore becomes essentially minus m alpha square by 2 h cross square. Okay, so you have essentially, please note, single bound state. So please note your energy state, okay, sorry, your potential is infinitely deep at exactly one position, right? You have one bound state, okay, and that bound state is essentially minus m alpha square by 2 h cross square. Please note your alpha has a part to play over here, all right? So your potential was what? Minus alpha delta x, right? So let me just remind you once again, what was your potential? V of x was equal to minus alpha delta x. Okay, so this alpha has a part to play in your energy. Okay, please note that, right? Yeah, so it's a very interesting mathematical finding that you do have a bound state. Okay, even though the potential is infinity, okay, or minus infinity uh, at exactly one position, and the factor that multiplies it, that tempers that delta function, has a role to play in the value of the bound state energy. Okay, so this is a pretty interesting finding, I would say. Okay, so now the point is that how do we go about finding the B? Yeah, the B uh, is essentially you will have to normalize, right? I should have said, this kind of garbled up my earlier sentences. I said that we'll get a handle on the B. We will be getting a handle on the energy, not B. B we anyway get by. Once we have an idea of what this situation is, we can get a handle on B by doing a normalization. So let's go ahead and do a normalization. Okay, so so yeah, normalization, normalize to get B. Right? And how do we do this? Of course, it is you have to go as usual from minus infinity to plus infinity. Psi of x whole square dx should be equal to 1, which implies that you will get. Um, so what you can do is, um, so this is how I have done it at least. Just d mod b square e to the power of minus 2 kappa x dx is equal to 0. So which implies that 2 mod b square integral 0 to infinity e to the power of x dx is equal to 1. Okay, so this we can write it as so. Yeah, so I think what I finally got was something like minus mod b square divided by kappa, like 0 minus 1 is equal to 1. So which implies that mod b square is equal to kappa, which implies that b is equal to root of kappa. Okay, so which of course you can put in the value of kappa now, and what you end up getting is essentially m square alpha square to the power of h cross to the power of 4, I think. Yeah, you get under root. Okay, this is what I have written, but of course you can simplify it further. All right, so let's just do that. Okay, so you get essentially this should be equal to root of m alpha by h cross. Okay, so this is your value of b. So therefore now your psi of x, okay, essentially will be nothing but root m alpha by h cross, and then you have e to the power of minus m alpha by h cross square. Okay, and you can say mod x. All right, and what is your bound state energy? Once again, so that I have already put. Try and remember this. Okay, this is a, sometimes you're given this and said what kind of potential will produce this kind of a wave function. It's a little important to remember this. Okay, and since I've given you that picture, all right, earlier of the wave function, that should help you spot, okay, the response, what kind of wave function is apt for a delta function potential. So kindly, I think, remember this, and also this particular, the single bound state energy. All right, so now let us look at what, how a delta function potential will influence a scattering. Okay, so you can have a scattering of a delta function potential as well. And for this, of course, so let's look at the scattering states. Though I don't think I have any problems which I have given you with the scattering state, have I? I'll have a look. I don't think so. Okay. Most of them, I think, are problems with the bound state. But nonetheless, it's a little useful to look at the scattering state because you never know, right? So this is, of course, when E is greater than 0. And how does your Schrodinger equation then change? Okay. So you have h cross square d square psi by dx square. And then, of course, you have minus alpha delta x psi x is equal to E psi of x. All right, so for x less than 0, what will we have? We'll have h cross square by 2m is equal to E psi x. So which implies that, of course, sorry, I mean, this is all old hat for you guys, is equal to minus 2me by h cross square psi of x. Okay, so which we will write as equal to d square psi by dx square is equal to minus k square, correct? Psi, which implies that your psi of x will be essentially some a e to the power of ikx plus b e to the power of minus ikx. Okay, and what is your k? I will just write over here. Your k, of course, is equal to square root of 2me by h cross square. So this is, of course, you're getting into your plane wave solutions, right? I mean, for all scattering states, that is indeed the case. And then you have modifications of the k, correct? So let me change the... Right. So now what is your... yeah. And then similarly, so let's just do the other thing. Similarly, if you had your, let us say your x greater than 0, then you would end up with the solution psi of x is equal to some f e to the power of I k x plus g e to the power of minus ikx. Note over here, I mean, it will stay bounded no matter how far you go. Okay, plus infinity, minus infinity, not a problem. Uh, so let's, yeah, because both of them are oscillatory solutions, right? Yeah, whether it's e to the power of ikx or e to the power of minus ikx, they're both oscillatory, so they don't blow up. So now let us look at for the continuity conditions. Okay, so continuity conditions. Okay, so when so continuity, so let's do it first for psi, okay, at x equal to 0. And what will we end up getting? We'll essentially, if you remember, we had an a e to the power of ikx plus b e to the power of minus ikx. So you'll just get an a plus b equal to, and then for the x greater than 0, you'll just get an f plus g. Okay. Then the second one is for d psi dx. And what will we get essentially? You will get an ik, okay, and here you'll get an a e to the power of ikx minus minus b e to the power of minus ikx, right, is equal to here also you will get this is for at x is equal to 0, uh, which is equal to ik a minus b. And this is, of course, for x less than 0, right? And similarly for the region x, so this is for x less than 0. And if you want to do it now for x greater than 0, you'll have essentially ik, so f, right? That's what I wrote, ikx minus g to the power of minus ikx, okay, at x is equal to 0, which becomes essentially ik f minus g. This is for x greater than 0. So for your continuity conditions, so we will use the same trick. Okay, we cannot expect a continuity because your potential has gone off to infinity, right? So let's now look at what the delta psi of x is going, d psi dx is going to be, which is going to be essentially the d psi dx approaching x from positive 0 minus d psi dx x going to it from negative side of 0, right? So which will become essentially ik will be there, and this will be F minus G minus A plus B. Okay, so this is what we get, right? Now, what is, of course, your psi of 0? Okay, if I just do it from the your A plus B is, as you can see from over here, your A plus B is equal to F plus G, right? Yeah. So we know that your psi of 0 is, we can just put it as A plus B. Okay. So yeah, and also your just hang on a second. I'm getting into some, I've written something here which is not making sense to me anymore. Usual problem with SB ma'am. I think you all know that, right? Oh, okay. I didn't realize I've gone past my time. Okay, so just give me 2 minutes. I think I should be able to clarify this soon. Yeah. Um, yeah. So if you remember the treatment that we did, okay, for your what do you call, where we kind of took the Schrodinger equation, and what did we do? We basically um, we integrated it, right? Integrated it and took limits, right? You remember that result? That was anyway a general thing that we worked out, right? So that result should hold good even over here. So we thereby know that your delta d psi by dx, okay, should be equal to minus 2m alpha by h cross square psi of 0. Okay. So therefore, your minus 2m alpha by h cross square psi of 0 is equal to ik f minus g minus a plus b. And please note, this implies that minus 2m alpha by h cross square, and here you will have a plus b is equal to ik f minus g minus a plus b. Okay, so this is what we get. And then okay, so I seem to have really botched up my notes very badly over here. Okay, I seem to have done some real nonsense over here. Okay, so what we will do is just hang on a second. Yeah, I think I ran into trouble last time also trying to do this. Okay, I think I'm already running out of time. I will try and send this guys over to you guys. Okay. Yeah. I'm sorry about this. Essentially, you can write down your F and G in terms of your A and B. All right. From this, and you can go ahead and write down the scattered state solutions. Okay. So I will send you the rest of the working out of this. All right. I will end this over here right now, because I see that I have already 6 minutes beyond my permitted time. So I will stop the share right now. Okay. And I'm requesting those people who are yet to send me the solutions of the simple harmonic oscillator to kindly send it over to me, so that maybe if not in the next class, at the next to next class, we can sit and discuss all the problems that have been solved. I mean, what I will do is I will look through your thing and I will discuss what I saw as I would say errors, or if there is some overall method, people have had trouble with a particular kind of a problem, then I will discuss that. And if I see some interesting new solutions, I will say talk about that as well. Okay. So fine, I will stop the recording right now.